Okay, so this is the second part of the notes on gas law. So this is going to be picking up with the kinetic molecular theory and going through the end of the slides. All right, so in the first part of the lecture, we focused in on the algebra, on the conversions between pressures. We looked at the differences in Charles and Boyle's law and Gay-Lussac's law. We looked at the combined gas law. We talked about the ideal gas law, right? And we solved some problems that were associated with those. In the second part of the video, we're still going to look at a little bit of math, but we're also going to look at explaining the behavior of gas in terms of molecules, right, at the molecular and submicroscopic levels. So kinetic molecular theory describes, or is the theory, sorry, that describes the behavior of a gas as a bunch of molecules that are moving. So it says that matter consists of particles, either atoms or molecules, and they're always moving in random ways, and they're going really fast. The volume occupied by those particles is not really going to affect their behavior. Now, this is an assumption. This is not, in fact, true, but it is true enough, right? The particles of a gas are so small that the volume of space they take up doesn't really impact their behavior a lot. We assume that the collisions between particles are elastic, and what that means is they hit each other and they just bounce right off right away. This is also an assumption that is not entirely true, but the influence of intermolecular forces of attraction when two particles collide is really small. And so for kinetic molecular theory, we're going to assume it's zero. And that means the collision is just elastic. They just bounce right off. Now, as we said, we're going to assume that the attractive forces between particles, so not only when they collide, but when they're close together, have a negligible effect on their behavior. So we're not going to take that into account. And we're going to know, hey, gases don't have a fixed volume or a fixed shape, but they are going to take the shape and the volume of whatever container we put them in. The final assumption of KMT is that the average kinetic energy of the particles is going to be a proportional relationship to their Kelvin temperature. So the hotter a gas is, the faster the particles are going to move on average. And that makes sense. But what you may not realize is that not all of the particles of a gas are moving at the same speed, even though many of them or all of them are at the same temperature. And so this graph right here, which we call a Maxwell-Boltzmann distribution, is a graph that shows us the average number of particles moving at a certain speed at a given temperature. So let's kind of break this down and see what we're looking at. So on the y-axis, we have the relative number of particles. So the higher the value from the y-axis, the more particles are moving at that speed. The x-axis is the molecular speed in meters per second. So at 0 degrees Celsius, many of the particles are moving, we'll say, what's that? About 1,500 meters per second. But that's not all of them, right? There is a bell curve looking thing kind of here. There's a very small percentage that are moving almost zero, right? And there is a very small percentage that's moving above 4,000 meters per second. But overall, the majority of the particles at 0 degrees Celsius are moving. The average molecular speed, right, this midline, is our 1,500 meters per second or whatever it is. Now, if you add heat, then you take the curve and you stretch it, like you literally pull it out. And when you pull it, the top is going to drop, all right? And it's going to flatten out the curve. And so at 500 degrees Celsius, the average molecule speed, right, we'll say it's, 2,700. You still have a couple molecules that are moving very, very, very slow. You have quite a few molecules, right, that are moving even faster than 5,000 meters per second. And so an increase in temperature spreads out the distribution of the molecular speeds, and it's going to shift the speed upwards. It's going to shift to the right. And we see that, right? The average here was 1,500. The average here was, we'll just say, 2,700. And so there's definitely a shift to the right. That also means that each particle, on average, has more kinetic energy, right? The faster something is moving, the more kinetic energy it has. So heating up a particle of gas or a particle of solid or any particle imparts more kinetic energy to it, and on average, a higher molecular speed. Now, if we compare the same gas at different speeds, we get this graph. If we compare if we add another temperature to it, we can have a third curve. So in this first one here, I only have nitrogen, and I have it at 100 Kelvin, 300 Kelvin, and 700 Kelvin. Now, what I'm seeing is that at a low temperature, I have a pretty low average speed. At a higher temperature, right, I have a higher speed. And at my highest temperature yet, I have a higher speed, right? The distribution of speed for nitrogen gas is going to change based on its temperature. That's what we just said. Now, what if we want to compare different gases at the same speed, okay? Now, we get a very similar shaped curve, but it's really important to note that in this graph, we're talking about three different gases all at the same speed, right? 300 Kelvin, or at the same temperature, rather. Compared to this, two different graphs, they're very, very similar. Make sure you know which one you're looking at if you're answering a question about them. Now, what do we see in this second graph? And I'm going to move my face out of the way. Well, the first thing that we see is that chlorine gas is the heaviest gas of the three that we've been given. It's almost 71 grams per mole. It's also the slowest. Nitrogen is the second heaviest. It's in the middle. It's the second slowest. And helium is the lightest of the three gases, and it's the fastest at this temperature. There is a relationship between the gases that is based on their size, based on their molar mass, and it is called the root mean speed. And it is equal to the square root of 3RT over fancy M. Now, we've seen all of this before, right? That's the molar mass of a gas. Temperature has to be in Kelvin, right? And R is our 0.0821 or liters, atmospheres, whatever. So these are all things that we've seen before. But now we're looking at their root mean speed, okay? And that tells us how fast they're going. That's the U. The U is this number. This is the number that you're getting. So 1,500 or 2,000 or whatever it is on the x-axis. The heavier a molecule is, the slower it moves. Now, why might that be? Well, diffusion is the mixing of molecules when one gas interacts with another gas, right? So it's two gases kind of mixing together. Now we know that gases move at random. And this is a pretty interesting picture because on the left we have ammonia, and on the right we have some hydrochloric acid. And we note that hydrochloric acid is heavier, right? This is the heavier gas. And so we would expect the gas to not move as fast, right? HCl gas will not move as fast. Now, what you're seeing above the HCl that looks kind of like smoke is not actually smoke. It's NH4Cl. It's ammonium chloride. And so this is a reaction that is occurring. NH4Cl. Let's do this, sorry. NH3, let's do it the right way, plus HCl forms NH4Cl. So what can we glean from this that's related to diffusion? Well, we've taken the tops off the tube, and obviously we know that a liquid, right, ammonia is a liquid at room temperature, but it does have vapor pressure, and so some of these molecules are escaping, right, and they're moving out into the environment. Same thing is true of hydrochloric acid. Some of that is moving out into the environment, but this one is slower. Now, in order for a reaction to occur, we know that at a reaction, or that for the reaction to occur, the molecules have to impact each other, right? They have to hit. So look, if we draw a line down the middle, where is the majority of the reaction occurring? Well, it's really obvious that it's on the right side, right? Well, why is that? Can we explain it in terms of diffusion and root mean speed and, what we were just looking at on that previous slide? Well, yeah, absolutely. So if I was to graph these two, I would expect HCl to look like this and my ammonia, NH3, to look like that. NH3 is faster because it's lighter. And so it's able to cross this midline before it interacts with the HCl. And so all of my NH4Cl is kind of stuck around here because that's as far as the HCl has gotten, right? It hasn't moved as far. So that's an interesting kind of visual application of this. Now, there is a slight difference between something we call diffusion, which is when gases just mix together, and effusion, which is when gases move through a tiny hole. And Graham's law is what we use to describe effusion. And it's really a simple law. It says that the rate for A divided by the rate for B equals the square root of the mass of B over the mass of A. So we have a little cross multiplying going on here, and we have the square root symbol. Now, what we find is that the rate of effusion is inversely proportional to molar mass. So what's that mean? Well, it means the heavier the gas, the slower it moves. It's got like a great big molecule has to fit through that tiny hole. It's got to hit it, and get through there, and it's going to do that less often than a smaller gas, right? The smaller gas can just zip right through the hole, where a larger gas, the molecule actually has to be oriented right to fit through the hole. And so the heavier the gas is, the greater the molar mass, the slower it's going to effuse. Now, let's look at a problem like that. It says a mole of oxygen gas and 2 moles of ammonia are placed in a container and allowed to react at 850 Celsius according to this equation. Using Graham's law, what's the ratio of effusion of the rates of ammonia to oxygen? All right, well, this is pretty simple. We take the rate of NH3 to the rate of O2, so we put it on, NH3 on top, O2 on the bottom, because it says effusion of NH3 to O2. So that means this goes on the top and this goes on the bottom. And then we set that opposite to the mass of O2 over the mass of NH3 with our square root bracket. And so we get 32 over 17. We divide that and we take the square root and we get 1.37. So what's that mean? Well, NH3 is 1.37 times faster than O2. And that makes sense because O2 is heavier than NH3, right? And we just said that the heavier the gas, it goes slower. So NH3 is faster by a factor of 1.37. That's it. That's all we got. It's pretty simple stuff. Here's another one. What's the rate of effusion, of hydrogen if 15 centimeters of CO2 takes 4.55 seconds to effuse out of the container? All right, well, the rate for CO2, rate is just how much is moving and the time. So 15 centimeters cubed divided by 4.55 tells us that 3.3 centimeters cubed effuses per second, moves per second. So we have a speed. Well, I have a rate, right? Cm cubed over S1, so over S, so that's the same as S to the negative 1, the inverse, equals, and I have the two masses. How do I have the two masses? Think about it for a minute. If I have a formula, I just go to the periodic table. And that gives me the mass, right? 2.016 grams per mole for there. And this would be 12.011 plus 31.998. So that's going to be like 44.001 or something like that. I don't know. 44. Yeah, there we go. We can round it. So this tells me that the rate of H2 compared to the rate of CO2 is 15.5 centimeters cubed per second. So that's it. That's what we're doing there. All right. You can try this one. So take a minute, try to figure out the molar mass of some gas X if it is effusing 0.876 times as rapidly as N2. Now, I'm going to let you do this one. So pause it, solve it. But before you do, something to think about. It's slower, right? 0.876 times as rapid. So that means it's slower, right? One would be the same. So it must be heavier than N2, right? So if N2 is 28 grams per mole, right? Because nitrogen is 14.007, then it must be heavier than 28. So if you don't get an answer heavier than 28, you know you did it wrong. So pause it, try to solve it. Okay, I'm going to assume you pause it. Now it's solid. There it is. So I'm taking the ratio right on the right, the rate of X to N2, and I know that that is the molar mass of N2 over the molar mass of X. So I know N2 is 28 grams per mole. I know the rate, it gave it to me, 0.876. So if I want to get rid of a square root, I need to square both sides. So I square it. That gets rid of the square root, cancels it out. Now I need to just solve. So divide, or you can do one of two things. You can either flip it, which is what I would do, or you can multiply both sides by m of x and then divide by 0.876 squared. Anyway, m of x equals 28 divided by 0.876 squared, and that tells you 36.5 grams per mole is the molar mass of your gas. Now, these are pretty simple, just ratios, right? And when it comes to effusion is a great way to describe how fast gas moves. The big takeaway here is this. Bigger gas molecules move slower than smaller gas molecules, right? That's what we're after. That's the understanding we want to have. Now, I do like to point out that, because this is chemistry honors, we go a little bit deeper into the difference between an ideal gas and a real gas. So an ideal gas obeys those tenets we talked about at the beginning of kinetic molecular theory. And we use the gas laws that we've talked about to talk about ideal gases. But in reality, there's really no such thing as a perfectly ideal gas. Under normal conditions, all right, that's close enough to give us an approximation, but it's not actually true. When you start to get under extreme conditions, really polar gases especially show deviations from your ideal expectation, all right? So in an ideal gas, we know that the particles are in continuous random motion, right? This is a little recap. We know that the particles collide with no loss of momentum, so the speed doesn't change. It's a perfectly elastic collision. We know that the volume occupied by the particles is basically zero, right? We said that the particles don't take up a lot of space. So when we compare that to the huge volume of the container, we just basically treat it like it's zero. The particles aren't attracted to each other and they don't repel each other, which we know because we've talked about intermolecular forces can't be true. But for an ideal gas, that's what we say. And we say that the average kinetic energy of the particles is going to be proportional to their Kelvin temperatures. Now, again, at normal temperatures and pressures that we see in our day-to-day lives, gases are going to approximate this. But once you get outside of those normal pressures, then you start to get huge deviations. So this line right here that's nice and flat, that's the ideal gas, okay? And you can see down here on the x-axis, we have pressure in atmospheres. Well, one pressure in atmosphere is like right there, right? That's normal. When you start to get into like 100 atmospheric pressure, gas starts to be funny, especially these guys, right? Like your N2, and that dark blue line is Cl2, and that might be, I can't tell if that's CH4 or CO2, but those four especially, right? So in real life, like it's important to understand, there is no such thing as an ideal gas, okay? That's just not there. We need to be able to explain why those deviations occur. Well, it's pretty simple. Real gases don't actually have zero volume, and polar gas particles will attract if you compress them. So when the pressure goes up, you're compressing the gas, right? And polar particles, which have, right, when you see polar, think dipole moments, all right? Well, a dipole moment is going to attract each other, and those forces of attraction are something that you would have to overcome if you want the gas to do something. Like if you want the particle to move, it's got to pull away from that force of attraction. That slows it down a little bit. Now, there is an equation of the PV equals nRT equation, of the ideal gas equation, that accounts for this, and it's called the van der Waals equation. Now, you do not have to memorize this equation. I want you to know it exists. I want you to see me use it. You don't have to memorize it. It would likely be an answer to a test question, though, like which equation accounts for the real behavior of gas? Well, that would be the van der Waals equation, okay? Because it accounts for the deviations from ideal behavior because a gas has a volume and does undergo intermolecular force attraction. Now, in this, you have A, which is the attractive force between molecule, and B, which is the residual volume of your molecules. A and B are in a table in your book. You can look them up. Not something you have to memorize, right? So let's use it. All right, it says, what is the volume of CO2 produced at 37 Celsius and 1 atmosphere when 5.6 grams of glucose are used up in the reaction? Okay, so we have a stoich problem here. Well, the first thing we need to do, all right, is, pause it and work it. So give it a shot. Try to work this on your own. I mean, I think you guys are capable of this. So give it a pause and work it out. All right. Now that you're back, let's do this. So we need to go grams to moles and then moles to volume. All right. That's what I need to work out here. So I've given 5.6 grams of sugar. I'm going to use the molar mass of sugar to convert grams to moles. I'm going to use the moles in my balanced equation, the molar ratio, right, 1 to 6, to go moles of sugar to moles of CO2. Those are going to cancel, all right? And that's going to give me 0.187 moles of CO2. My volume is nRT over P. And so now I'm going to take that volume, all right, or that number of moles, rather, and I'm going to plug it in for N, and I'm going to solve for V. So the problem gives me a temperature. It gives me a pressure. I know R because it's a constant, and this I just found right there. So my volume is going to be, when everything cancels, 4.76 liters. Excuse me. Oh, gracious. All right, sorry about that. So I have 4.76 liters. There we go. There's what I made. There's my volume of CO2 produced. Try this one. All right. What is the volume of CO2 produced at 37 Celsius and 3 atmospheres? So all we've done is change it from 1 atmosphere to 3 atmospheres. So I'm going to plug it in the exact same way. So I'm still going to solve for my volume. Still going to solve for my moles. It obviously hasn't changed. Still going to solve for volume. I'm just going to change everything except now I'm putting in 3 atmospheres. And what do we find happens? Well, I make less, right? It's compressed. So I made the same amount of CO2, but the volume that it occupied is less. And that makes sense, right? Because we're under greater pressure. So the nice thing about a volume, or the nice thing about a Stoich problem in the gas law unit is, it should make logical sense, right? So that's a good thing to fall back on. Now, we're not going to do a problem that has anything to do with the van der Waals equation. I've, kind of taken that out because that's something we do in AP. We do use the van der Waals equation in AP. But now that you're aware of it, you can use it as an answer. You have that foundation. That's a good thing. Now, there is a lot of gas in the universe, right? I like to finish the gas equation or the gas lecture with pointing this out. So these are called the pillars of creation. They're part of the Eagle Nebula. They're something like 7,000 light years from Earth. This is a picture from the Hubble Space Telescope that's kind of been zoomed in. The left pillar is 4 light years tall. All right, now think about that. Light travels 186,000 miles per second. And it would take 4 years traveling 186,000 miles per second to go from the bottom of that picture to the top. That's a lot of gas. The green colored gas, this is a false color image. The green colored gas is oxygen, okay, is hydrogen. Red is sulfur. You can see a lot of that red here, there, a little bit at the bottom here, and kind of mixed in. All right. And the blue is oxygen. It's actually oxygen 2+, which is called dioxygenol, which is a really interesting oxygen species. There's a lot of gas. There's probably more gas than any other phase of matter in the universe. So the conversation about gas in chemistry is pretty important. All right. So hopefully you enjoyed looking at this picture, and hopefully you understand some of the things we've talked about. If you need help, send me an email. I'll be glad to give you guys a hand. All right. Again, you may need to watch this more than once. That's not a bad thing. Go back, rewatch, take notes as you go. That's what being a student's all about, right? So if you need to watch it more than once, do so. If you need help, send me an email. All right. I want to help. All right. But I can't help you if you don't email me. So reach out and I'll be glad to help you. All right. So I'll see you guys in the next video.